Hi everyone, welcome to my channel and welcome to this video. So in this video we are going to talk about a specific kind of sockets in computer networks which is extremely powerful and which allows us to go a level deeper into the TCP IP stack or the OSI stack. Usually the most popular, the most common type of sockets that we come across while working in computer networks are the stream type sockets and the datagram sockets, which belong to the AF INET socket family. The stream type socket, we use it for usually for the TCP protocol, and the datagram socket we use it for the UDP protocol. So these are the two most popular protocols of the transport layer, right, which is used in the OSI networking stack, right? So TCP, we use TCP when we want a reliable connection oriented type of connection, and we use datagram sockets or UDP when we want a connection less socket, right? We don't want to pre-establish a connection, but we just want to send the packets. However, the type of socket that we will be discussing today is raw sockets, and a specific form of it, which is also known as packet sockets. These sockets help us to dig deep into the network stack and the network layers, and they allow us to directly access the headers of the packet at various levels of the stack, networking stack. And in order to understand the power and the utility of this raw socket or packet socket in a better way, we'll try to create a packet sniffer using packet sockets, and we will use that packet sniffer to monitor the packets that's entering or leaving our machine on different interfaces. We'll also add various filters to a sniffer. Let's say I want to monitor only, or I want to filter only those packets which are coming from a specific port, or which are coming to a specific port on my machine, or which are coming from a specific IP. We will have an option to filter only TCP packets or UDP packets and like that, right? So this entire sniffer, this entire packet sniffer, we won't be using any external library or anything external. We only be using simply pure C code and packet sockets to create this. We'll be building it for the Linux operating system, and we'll be using only C code, nothing else. So yep, as always, let's get started. Okay, so before jumping into the raw sockets or the packet sockets, let's once look at an overview of how most of the stream sockets or the datagram sockets work in the Linux kernel. So I won't dig deep much because lots of manuals and documentations are available on these topics on the internet, but to just get started with it, usually when we want to, let's say, receive or send a packet, a network packet from our machines, the first step with which we start is creating a socket, right? So in our application, let's say in C or Python, in whatever language of our choice, we first create a socket, and let's say we are creating TCP socket. So for TCP, what we do is that we first mention the family, which is usually AF INET. Then we mention the type of the socket. So in this case, we will use a stream socket. Again, I'm just using pseudocode. The constant names might vary. And then we want to specify the protocol. Usually there is one protocol per type of socket. So we don't mention them, but in case a type of socket has supports multiple protocols, then we need to mention the particular protocol. So in this case, let's say we are using TCP because stream sockets are used for TCP. So that's the first step. We create a socket, and then if we want to receive some data or send some data to a remote host, which is acting as a server. So again, any peer can act as a server or a client. TCP is a two-way peer-to-peer protocols. So any peer can act as a server, and the same peer can act as a client as well for another server. So let's say that this is a client, and it wants to receive some data from a remote server. So what it would usually do is it can bind to an interface, right? It binds to 10.10.1.2. It can be any interface, any live interface in your computer, and it binds to a port. If you don't mention a port here for a client, any random port can be selected and will be selected by the kernel. So let's say we are binding to 55556. Then you usually make the connect call. So in connect, you mention the server, again an IP and a port, right? And once the connection is successful, so the TCP will do its three-way handshake, and once the three-way handshake is successful, you would want to call the RECV or receive call, right? And you will provide a buffer over here, You will provide a buffer where the data will be stored, where the received data will be stored, and then once you have the data in the buffer, you can do other stuff with that data, whatever your application wants to do with it. If it's a UDP socket or it's a datagram type socket, like this initial connection with the remote host is not required. Since it's a connection-less protocol, it doesn't need you to pre-establish a connection to your remote server. So connect is not required. You can simply use the receive from syscall to start receiving packets from your desired remote server. So anyway, so these are the primary steps that you need to use or you need to perform in order to receive a packet of data from a remote host. Now if we translate this to the OSI stack or the TCP IP stack, so the first layer that we have is the physical layer, right? So this is the layer where the actual data is going or is being transmitted in pretty much in your binary. This is the bottommost layer where your data is actually transmitted. In many stacks, it's combined with your data link layer, like your Ethernet, but the OSI abstraction denotes it as a separate layer. Then comes so in physical layer, the unit of data is usually bits, right? And then comes your data link layer. One of the most popular protocol here is the Ethernet protocol, right? And the unit is frames. So whenever we talk of data in this layer, usually we use the word frames to denote unit of data. And then on top of this comes the layer 3 or the network layer, where the IP routing, where the most popular protocol is IP protocol and the unit of data is packets. And all the routing and everything happens at this layer, right? And then comes the transport layer, like transport. As I mentioned, two most famous protocols here is TCP and UDP. Unit of data in this layer is usually segment. And on top of this, we have session layer, presentation layer, and finally the application layer. So we won't be bothered much about these three layers. So we won't be discussing much about these three layers. So we'll be only focusing on these 4 layers. So usually what happens is that when a packet arrives at the physical layer, and again when if you look at the TCP IP stack, several of these layers are combined, but we'll just use this abstraction to understand stuff. So once the data moves to the data link layer, usually, let's say in case of a TCP packet, remember, although we are calling it a TCP packet, in this layer is just a frame. So what data link layer will usually do is, or rather I should say, once the packet arrives at the data link layer, what the kernel would usually do is it will strip off the headers that is required for the functionality of the data link layer. So in case of Ethernet, it will strip off the Ethernet headers from where it will get the MAC address. Right? So MAC address is basically the physical address of your NIC or the NIC card that's attached to your interface. And that will pretty much tell the kernel whether this packet is meant for this machine at all, right? So it will strip off this header, and the data that's present in that frame, after stripping off the header, whatever data is left, it will send that to the network layer. So what the network layer would usually do, if it's running IP, the internet protocol, what it will do is it will strip off its required headers, and which will usually have the source IP address and the destination IP address. So again, in the data link layer as well, there will be a source MAC and the destination MAC, right? So basically, when the data is going up the ladder or up the layers, the kernel will at the data link layer will check that whether the destination MAC address is matching with the MAC address of the machine. So again, from here it will strip off the source IP and destination IP, so SIP and DIP. And depending on the destination IP, it will take a decision whether it's meant for this machine, or it might do a routing depending on the route table that's available. So it might find out the next hop for this given destination IP. Right. So it will strip off its required headers, and then again it will send it to transport layer. Transport layer will strip off its headers. Those headers will contain the source port and destination port as well. So determines to which application the data will be sent to. So transport layer will strip off its own headers, and then it will go to session layer, presentation layer, and finally to the application, right? So that's how the data bubbles up, and same thing happens when it comes down. So before sending data from transport layer to network layer, the kernel will put the ports and the other transport layer headers. Then from network to data link layer, it will put the IP headers. From data link layer to physical layer, it will put its Ethernet headers, which is the source and destination MAC and the other stuff. That's how data goes up and down, right? So if you see, like in all these layers, a lot of work is done by the kernel. So kernel is basically parsing the packet, analyzing the packet, finding out various things about the packet, and then the data part, the pure data part which is required by the application, that's being sent to the actual application, right? So the application as such is not bothered with the headers in this case. Like it doesn't have access to all the headers. At the same time, it's not bothered with them. All it wants is the actual pure data. But what if we want to dig deep into the packet? So let's say I want to dig deep and I want to get access to the headers of the lower layers as well. For example, for the network layer, for the IP headers, I want to know what's the time to live, what's the header checksum, or let's say what's the total length, or what's the type of service. Or let's say for the transport layer, for the TCP protocol, let's say I want to get access to things like what is the value of the urgent flag or the acknowledgement flag or the sequence number and things like that. So what if I want to get access to this kind of data for the different layers? What should I do? So in cases like this, we can take help of a different type of socket, which is also known as the raw socket. So a specific type of raw socket is, or I should say a specific flavor of raw socket is the packet sockets. Packet socket even lets us access the header information of the data link layer. So with raw socket, you are limited till the network layer header information, network layer and transport layer. So network layer and above. But with packet socket, you can go even a layer deeper and you can access the data link layer or the Ethernet layer headers, right? So you can access that as well. These are the type of sockets, packet socket and raw socket, which will allow you to dig deep and play around with this kind of lower layer header informations and data. So to use these sockets, if you just want to use the raw socket and not the packet socket, you would have to define your socket somewhat like this. So for the simple raw socket, your family remains the same. It's AFINet. For the type of the socket, you need to mention sock raw. And if you want to read using this socket, then you will have to mention the type of protocol you are using over here, that is TCP or UDP. That is IP proto TCP or IP proto UDP. Or if you want to write, or that is you want to send data using this socket, then you will have to use something like IP proto raw. So here's the catch with raw sockets. You can't use the same type of socket for both read and write. For the simple raw sockets, you can't use the same socket for both read and write, but depending on the protocol, depending on the value in the protocol field, if it's IP raw, IP proto raw, you can write with it but not receive. Or if you mention the exact protocols, that is IP proto TCP or IP proto UDP, you can read that protocol data using those sockets. And now if you want to go a level deeper, that is to the data link layer, and let's say you want to read the packets data link layer header information as well along with network and transport, what you have to do is you have to use socket. Instead of AFINet, now you will have to use AF underscore packet. The type remains same, and that's why this is also a raw socket. The type remains sock raw, and you will have to mention what the protocol of the packets you want to capture. Usually a very common option here is htons of ETH underscore T underscore all. So basically you are capturing all kinds of packets. So the other options available here are the other specific protocols. For example, maybe 802.3 protocol packets or ETH IFP underscore IP, which stands for only the IP protocol packets. But there are some catch with those, which we will discuss when we build our sniffer. So for the timing, we'll go with ETHP all. And at the software level or at code level, we will filter out anything apart from the IP packets. We will capture only the IP packets. And what's H2Ns, or what is htons, or also H2NS? It's basically, it converts the byte order from host byte order to network byte order. So usually hosts on our systems is Little Indian, right? And network byte order is always Big Indian. In case of that, it will simply convert the byte order from Little Indian to Big Indian. If your system by any chance is Big Indian, it usually does nothing. But for other systems, for example, my system, it's a Little Indian system. Right now, I'm running a Intel processor, which I know it's a Little Indian processor. In my system, the htons will convert the Little Indian byte order to Big Indian byte order, and S just stands for short. So the ETHP all header is provided by the operating system, and we know that it's a short data type, which is 16 bits. Okay, so how does this raw socket work? So how does it get the raw data? So at a overview level, it's quite simple. Let me just make some space. At an overview level, how raw sockets work is pretty simple, but yeah, but that's only at an overview level. So let's say this is your NIC attached to your interface, right? The moment, let's say we have a application where a raw socket is running, and there has been a receive call has been made on this, or I should say a receive from call has been made on this raw socket, right? So in a loop, let's say we are continuously making receive call. So what happens is the moment a packet arrives, packet P arrives at the NIC, what the kernel will do is, after the usual processing that's done by NIC, like checking the checksum and things like that, what the kernel will do is it will take a copy of the packet and it will directly send it to the raw socket, from which it will get bubbled up to the receive from function, and it will go to your application, right? So now your application has the entire raw packet data available to it. But it doesn't stop here. So if it would have stopped here, the actual application that, let's say it's a TCP packet that came here, right? And there is an application, let's say your browser has requested this TCP packet from some web server, so that sends this packet to NIC, and the kernel will step in and it will do the usual packet processing, the frame processing, segment processing for the packet, and it will also send, after stripping off the usual headers and all, it will get bubbled up through the OSI layer or this TCP IP stack, and it will get sent to your browser as well. But at the same time, a copy of the raw packet without the header stripped off, like the raw packet without any alteration to the headers, that will also be sent to your raw socket, from which it will get to your application, which is using the receive from syscall on this raw socket. So that is how your application will get the raw form of the packet. Cool. And once it has got the raw blob of the data, how it will differentiate between the different headers. So all the header definition in form of structs are already available in the header files provided by the operating system. So your best friend or your best weapon that you have here is use those structures and typecast the packet into those structures, and you read those data, and then you go to the next header offset, and again you typecast it to your next header. Like, let's say first you typecast it to the Ethernet header, you extract the Ethernet header information, then you go to the starting of the IP header offset, right? You go to the IP header offset, you typecast it to the IP header structure, which is also provided by your operating system. Again, you extract the required information, then you go to the transport layer protocol, that is the TCP or the UDP header offset, and then you parse those data and so on and so forth, right? So that's how you get all the header information using raw sockets. Okay, so now that we kind of know what are raw sockets, what are packet sockets, and how they kind of work, we are at a better position to appreciate the utilities and the power they provide us or anyone who's into network engineering or computer networks. So with raw sockets, you can do multiple things, like you can do deep packet analysis, you can create tools, you can create packet analysis or packet inspection tools like a packet sniffer and things like that. And the other very important thing that you can do with raw sockets or packet sockets is you can experiment with your own protocols. You can create your own protocols or design your own protocols in the user land, not in the kernel space, but in the user land, to try out your ideas of a new protocol or something like that. Right, so these are all the use cases and utilities that raw sockets or packet sockets provide us with. Okay, so now that we know that what are raw sockets, what are packet sockets, how they work to some extent, and what they can be used for, Let's try to use them in action. So what we will do is we will create a packet sniffer in C using only raw sockets, I mean packet sockets, which as I mentioned is a variant of raw socket. We'll be using no external libraries but only raw sockets to create this sniffer. It will be a terminal based tool, and then we'll be creating multiple filters on top of it, right, to add multiple filtering on the packets, right? And all the output will go to a log file so that we can see that log file and see what are the packets coming to our machine or leaving our machine from our interface. One thing to be noted here, like when we are using raw socket, the system calls like the usual socket sys calls like your connect, bind, this kind of lose their significance, because all you need to do is create the raw socket and then use receive from to tell the kernel that you want to read from this raw socket. We don't need to use bind or connect syscalls at all. And one more thing is, remember, like since we are getting the raw data and the kernel won't care about the protocol or anything like that for the raw socket, so we'll be pretty much getting all the packets that are coming to all the interfaces connected to our system, right? So let's say right now in my computer I have only one interface, that is the one which is interacting with my Wi-Fi right now, right? So had I been using two active interfaces, then I would be able to sniff all the packets which incoming as well as outgoing that is coming on both the interfaces, both the active interfaces. It doesn't matter the number of interfaces. With the raw sockets I will have access to all the interfaces. So usually when a interface works in this mode, that it allows a socket or a application to monitor all the packets that's coming and leaving that interface, it's usually called promiscuous mode. Like promiscuous mode means that you can, like, that interface can be used for monitoring packets. So usually for promiscuous mode there is only one interface that switches this mode on, but unlike that, with packet sockets you can like sniff actually all the interfaces on your machine. You can sniff all the packets coming and leaving all the interfaces on your machine, right? But as of now we have only one live interface and we'll only use that. And one more thing is, in order to use raw sockets, a process should either be run as a user with effective id 0, that is root, or the process should have the net raw capability, that is cap underscore net underscore raw. So in this case we'll be running our process as root to use raw socket. So let's get started with building our packet sniffer. So as usual with any C program, I'll start with including a number of header files or headers. So let's do that. So a chunk of these header files will be used to provide us with the structures, which will allow us to extract header information from the packet. So let's do that. Yeah, so that's it for the header inclusions. So now I'll simply define a macro for a graceful exit, which will also print the error, if any. Okay, so next we'll define a struct which will hold all our filter options. Once we take the filter options from our user, we'll use this struct to store them. So for that, I'll define a type def. So we'll allow our users to filter packets by transport protocol. So that's T protocol. Okay, and I'll call this type def packet filter T. Next, we'll allow them to filter by source IP and destination IP. Source port and destination port. and also the source interface name and the destination interface name. Let's say I want to filter all those packets which is arriving at a particular interface or which is leaving the system from a particular interface. So basically source interface and destination interface. So basically we can map interface to the MAC address provided in the Ethernet frame header. So we will store the destination and source interface names here, and using this we will resolve the MAC address of those particular interface, and using those MAC address we can do a matching against Ethernet header of the packet we are receiving. Again, MAC is always 6 bytes or 48 bits. We will define two socketddr.in typed variables. We will use this as containers for the source and the destination IP addresses that we will be extracting from the IP header. So let's define those. Next, what we'll do is we'll define our getopt, right? We'll define our getopt structs so that we can take inputs for filter options from our users. And we start with our main function. Log will be the name of our log file, which again we will take as input from the user. Let's define a variable of type packet filter t, and we will populate the members of this struct as according to what inputs we get from our user. We'll just add some defaults. So this variable is just to pass to the receive from function. We'll malloc our buffer. Now let's define the packet socket. So as mentioned, the family will be if packet, type is raw since it's a raw socket, and we will use htons ethpll. So now I mentioned that we'll be capturing only IP packets, but here we are using ethp all. So the problem is if I use ethp IP here just to capture the IP packets, by design the kernel won't show the packets, or the kernel won't send the packets to this raw socket where the source MAC address is the MAC address of my machine. So that is in other words, it won't filter those packets which are going out, or the egress packets, or the packets which are going out from my machine, which are going out from an interface, right? So that's the problem, and it's not a bug, but it's by design. Hence we won't be using ethp IP, but we have to use ethp all, and then we have to filter ourselves for IP packets. So let's do a quick check that our socket was created. and we will exit. Okay, so now let's let's first parse the user input. Right, so I'll be using the usual get opt long, so that I can also use the long version of the options. So this is the main struct that will be used by get opt long. This is for source IP. Destination IP, source port, destination port, this is the previous two are source interface and destination interface if we want to filter by them. And then comes our log file, what name we want to give our log file. Last two won't accept any argument, but they will just decide it's we want to filter TCP or UDP. If nothing is provided, then we will capture both type of packets. I hope I'll not miss any, but okay. So I believe that should be it. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Cool. And two non-argument, that is T and U. Okay. You want to pass this struct, which is long options and null. So C equal to -1 will be the break case. Now we simply need to iterate over the options and take action accordingly. Instead of storing hard coding the TCP protocol and UDP protocol IDs or identifiers, we'll simply use the macros. Let's ident this. we need to convert the arc from string to integer. So a2i will help us with that. We'll use the normal dot notation for the IPs, hence no conversion. It's just the string that we want. So this will store the source and destination interfaces names if required, if provided by the user. And our log file name option, we will simply strcpy this into the variable that we created for holding a log file name. And finally a default, which will simply abort. Okay. Now what I would want to do is just display all the options that was inputted by the user, so that we know all the filter options are being stored properly and there is no error. This will actually help us for debugging. Later we can delete it if we want. Okay, so now we have logged everything, and in case user has not provided a value for the log file name, we will just give it a default value. So if this is 0, then we will just strcpy a nice name, which is sniffer log.txt. And we'll just fopen the file, and if we fail to fopen it, we exit. Okay, so before moving forward, what we need to do now, remember that we want to also filter by the interface name. So how do we know that a packet is destined for a given interface or a packet is originating from a given interface? So the only way you can know that is by comparing the MAC address of that particular interface that you're interested in with the MAC address present in the Ethernet header of the packet. If you want to filter that packet which is originating from a given interface, so you need to first find out the MAC address for that particular interface, and then you need to compare it with the source MAC address of the Ethernet header, right? So the first step here is to get the MAC address for a given interface. So let's take a small detour from our raw socket exploration, and let's see how we can find out the MAC address of a given interface. So I won't be digging in much, and I'll just be writing a utility function which will help us to do that. I will create a tiny function called void get MAC, and of course I need the interface name and a reference to the packet filter, because we'll be populating the MAC address, the source MAC and the destination MAC fields in the packet filter itself. So I'll create a pointer for that. And the type, whether it's source or destination. Accordingly, we will populate the desired field in the packet filter variable or pointer. So this is the struct that will get populated with our required data. And interesting part is, for doing this as well, we need to create a datagram socket. But it will be a one-time socket. As soon as we get what we want, that is the MAC address, we will close it. Right now what we'll do is we will define the socket family. So ifr.ifr.addr.sa family, and it will be if inet, like we are defining the socket family of the address, and then we'll copy the interface name to another field, that is ifr name, and then we will use this constant for the size, which is ifnam -1. Then in order to populate a request struct, or that is ifrec struct, using this socket, we will need to do a ioctl call. So ioctl fd, and the constant here, the ioctl number that we'll be using. So this parameter is basically the ioctl identifier we want to use, and we will do siocgifh hardware address. So basically this will get the hardware address for us for the given interface, and we pass the reference to the struct, and then we can simply close fd. And if we just go to the definition of this macro, so you can see that this macro or this ioctl number is used to get the hardware address. Okay, so now we are done with the socket. We close it now, since we have got what we wanted. And there is a typo. Okay, so let's do some checking now. So if strcmp if type is source, then we will copy to packet filter dot source mac, and what we will copy is the address that we received. So the hardware, the MAC address is available under this field called SA data. Else we could have done a more specific check, like if type is dest, but we'll just leave it as it is for now, like packet filter dot destination mac, and the same thing, we can simply copy this. Yeah, so that's it. So that's a tiny function to get the MAC address for a given interface. And also I'll write a tiny function, utility function, to compare two MAC addresses. The thing is that I just want to make sure that we compare only the first 6 bytes of the MAC address that's present in the Ethernet header. Like that we can avoid the junk that follows after that. So MAC we could have also copied the first 6 bytes from the Ethernet header's MAC address and then do a strcpy, but I'll just do a manual check right now. Let me know in the comments if you guys know a better way to compare two MAC addresses in C. But I believe it's just string check is enough. And the easiest, maybe, I don't know. So I'll just go till so it's simple enough. If mac1 I not equal to mac to I, then you just return 0. That's it. And you return 1 otherwise. So 0 means false and 1 means true. So mac1, mac2, yeah, that's it. So now we have both the functions for extracting MAC address from an interface as well as comparing to MAC addresses. Okay, now coming back to our filtering once again. So since now we have our MAC extraction function, we can use it in our filtering. So we just have to check if packet filter dot source if name has been provided, then we just need to call our get MAC function, and we pass the source interface name and a pointer to the packet filter, and we of course mention that it's for the source, and we can simply copy this. It will be test, and it's test. Okay, now we start with the main loop, which will continuously call receive from on the raw socket, and it will, once it gets the packet, it will process it. So I'll just create a variable for the sake of the receive from function completion. We won't be using it that much, but anyways. So now we will make the receive from system call or library call. So this should populate the buffer with the packet data, raw packet data, and if we see that buffer len is less than 0, then there is some issue in reading from the socket, which should not occur under normal circumstances, and we can exit if that happens. Fail to read from socket. And finally, when we have our buffer populated with the packet data, we can simply call a process packet function, which we'll define in a moment. And we'll send a reference or pointer for packet filter and our log file. And we need to flush the file since we are using fopen, which is basically buffered. So yeah, we need to flush it so that we don't lose data in case of a abrupt program exit. Okay, now let's define our process packet function. This is going to be like the main function which will do the packet processing, and it will call multiple other functions for logging the various headers. So we will define it as void process packet. The first thing we need is a event 8_t buffer, which is our packet data, then its len, pointer to packet filter, and our log file. Right, so we need to define this IP header length. In a moment it will be clear why we need this. Okay, so now here's the thing. So in the raw packet data, the data maintains a particular order. So first we have the Ethernet header, then comes the IP header, and then comes the transport layer header, right? And then finally comes the user data. So we need to parse the packet, or we need to extract the header informations in that particular order. So first we typecast it to the Ethernet header, we extract that thing, the Ethernet header properties, then we go to the correct offset, then we parse the IP header, and so on. So let's first try to extract the Ethernet header, for which we'll typecast the buffer to ETHDR. ETHDR. Okay. So ETH equal to struct ETHDR Okay. And again, remember, we said that we will do a manual check. If the network layer protocol is not IP, then we will not proceed because we only want to capture the IP packets. So the thing with these headers are one layer always has the information of what protocol the above layer is using. For at least for the data link layer, network layer, and the transport layer. So the Ethernet layer or the Ethernet header will have information about what protocol the layer above it is using, right? And similarly, network layer, as in the IP protocol, will have information about what sort of protocol the transport layer is using, right? So what we will do here is we'll do a N2HS and we will extract the H proto and we will compare it with 0x0800. So this is the constant which identifies the IP protocol, right? Or ETH-PIP. If the protocol is not IP, then we simply return. Next, we do the MAC address checking, and now we'll use our MAC CMP function. So if packet filter dot source ifname, so if we want to filter by source interface, so if that is not null, and if the source MAC is not same as the filtered interface's MAC address, then we simply return. So we'll do packet filter dot source MAC comma ETH dot H source equal to 0. If they are not equal, then it won't be captured. We simply return. And we do the same thing for destination MAC. If we want to filter the destination MAC address by an interface not equal to null, and then MAC CMP packet filter dot test MAC comma ETH dot H test equal to 0, that is they are not equal, which means we do the same thing, we simply return. So that's our MAC address filtering that happened there, or basically interface filtering that happened there. Source interface, source MAC, H source, destination interface, destination MAC, destination source, H test. Okay, cool. So we have done 3 filterings till now. We have filtered on the IP protocol, the source MAC, and the destination MAC. And now we want to filter on the IP addresses, like the source and the destination IP addresses of the packet. So for that, we need to extract the IP header. And before we can do that, in order to do that, we first need to get to the IP header offset, right? So that's pretty easy. IP header starts just after the Ethernet header. So struct IP HDR star IP equal to struct IP HDR, and it will be a pointer. So that will be the buffer start address plus simply the size of ETH HDR. And what will be the length of this IP header? Because we want to know the transport layer header offset as well, right? So for that, we want to know the length of the IP header. For that, we can't use the size of IP HDR because IP header has got some variable options. So in order to do that, what we can simply do is we can store the IP header length in our variable that we created, and we can simply do .ihl. It gives the number of 32-bit chunks that's present in the IP header, right? So 32-bit as in 4-byte chunks present in the IP header. So to get the total length in bytes, we simply multiply it by 4. So now we have the IP header length as well. And of course it won't be dot, it will be this. Okay. So now we want to extract the IP source and destination, right? Like the destination and the source IP addresses. For that, we are going to use the source ADDR and the destination ADDR variables that we defined. So sin addr.s addr equal to ip is addr, and we can't just work with the ip.saddr and ip.daddr because we need to use a particular function to convert it into host byte order, right? And that's the reason we need to take help of source addr and dest addr, basically socket addr in structs. And we'll do the same thing for test addr as well. So in dest addr sign addr dot s underscore addr, we will put the destination IP address, right? Okay, so looks like I've made a typo here. It will be struct, of course, because it's a struct. Okay, so now what we'll do next is, before proceeding further, we should apply our IP filter. So we should only proceed further if this is the packet which we actually want to process after passing it through our IP filter, right? That is, if the user has provided some source IP or destination IP filter, we should do the matching right now. So let's do that. So for that, I'll be defining a function very soon, but let's first write the check. So it will just take the packet filter. Remember, the source addr and dest addr are global variables, so we already have the filter IP function, will already have access to those. So here I'll simply pass the packet filter pointer, and if that, again, it will, for false it will return 0, and for true it will return 1. And if it is false, then I'll simply return. So now let's quickly define our filter IP function. So for that, we'll just define something called filter IP, and it will take that filter IP, let's just call it filter, and if filter dot source IP is not equal to null, that is, user wants to filter by source IP, and strcmp, so both are strings, we can simply use the string comparison function. And now here we can't just use, again, as I mentioned, we can't just use that ip.saddr, but we'll have to use the inet n2a converter. So basically it converts your IP address from network byte order to host byte order. So inet n2a source addr.sin addr, and if that is not equal to 0, so if strcmp returns a non-zero value, it means there is a mismatch between two strings, and it means this is not a packet that we would want to filter, and we will return 0. Basically, this is not a packet which we would want to process. Again, we'll do the same thing for the destination IP. If that is not equal to null, and strcmp filter.test IP, again n2a, is not equal to 0, then return 0. Otherwise, if all the filters pass, we know it's a packet that we want, and we return true. Okay, so coming back to our process packet function, yeah, so we have already used our filter IP, and next we will check for the protocol. So let's say we want to filter TCP protocol and we get a UDP protocol, we will reject the UDP protocol packet. So let's do that. If packet filter.t protocol not equal to 0, so the default option is 0, which means the user doesn't want to filter by protocol. If it's not 0 and IP dot protocol not equal to packet filter dot t protocol, we return we don't want to process the packet, and we are done with the IP and the protocol filtering. Okay, so now that we are done with IP filtering and the protocol filtering, one more thing that I'll follow here is that for now, for this sniffer, I will only consider the TCP and the UDP protocol for transport layer. So if user has provided no filters, then we will consider only TCP and UDP, and if it's any other protocol, we will just drop the packet. Drop the packet as in we won't process it. If user has provided a choice for TCP or UDP, then it's fine. Then we drop either or. Like if user wants to filter only TCP, we drop UDP and vice versa. But if user has provided nothing, we only consider the TCP and the UDP packets. So what we'll do is we'll create two structs, TCP HDR star TCP equal to null. This will store the TCP header if it's a TCP packet, and we will create struct UDP HDR star UDP and equal to null. So now if IP dot protocol IP proto TCP, if it's a TCP packet, then we will typecast the buffer starting from the TCP header offset to the TCP header struct or TCP HDR struct. So let's do that. Struct TCP HDR star buffer plus IP HDR len plus size of struct ETH HDR, right? So that's TCP. So what we did here is, like as I said, that IP HDR IP header has got a variable length, right? So we calculated the length of the IP header for this particular packet. We stored it in IP HDR len. So we started with the buffer, the starting address of the buffer pointer. With that we added the next header, that is the size of the Ethernet header, and with that we added the size of the IP header. So now we are at the offset or the beginning of the TCP header. Hence we typecasted the packet starting from this offset to a TCP header type. So now we will have to do the port filtering, right? Filter port, and once again in very short while I'll define the filter port function as well. And remember, we need to use N2HS. Again, we are converting from network byte order to host byte order for short, and we will do TCP dot source and we will pass TCP dot destination, and to this filter port function we will also pass this packet filter pointer. So we need to filter both by source port and destination port, right? So the user might want to capture only packets which are coming from a particular source port or which are arriving at a particular destination port. So that we did here. And else if IP proto equal to IP protocol equal to IP proto underscore UDP, same thing, we will typecast it to UDP HDR struct, and we will similarly calculate the header offset. Right, and once again we'll do the same thing. Filter port and N2HS UDP dot source comma N2HS UDP dot destination and packet filter. And if that is false, what we do is we simply return, right? Or else what we do is, else we simply return, because it's neither UDP or it's neither TCP, and we don't want to process packets for the other protocol as of now, so we simply return, right? So at this point we know that it has passed all our filters: the protocol filter, MAC, source MAC, destination MAC filter, source IP, destination IP filter, as well as source port, destination port filter, as well as the transport layer protocol filter. So at this point we can start logging. So before that, let's define our filter port function. Okay, so we have called it filter port, and it will take a source port, a destination port, and the packet filter pointer. And now let's start our filtering. So if filter dot source port not equal to 0, that is user wants to filter by source port, and filter dot source port not equal to S port, that is the packet's source port, then it's a false filter, like we return false. If filter dot destination port not equal to 0 and filter dot des port is not equal to D port, once again we return 0, hence we return true. Okay, so now before moving further with the packet process function, let's write the functions which will log our different header data, right? So let's start with the Ethernet header logger, or the Ethernet header logging function. And so logging Ethernet header is the easiest one because it has got lesser properties. And so let's quickly write that. We'll call it void log ETH headers, and we'll pass it the ETH header pointer. So we'll be using fprintf, and the first thing we'll log is the first we start with just a header saying that is the Ethernet header information that follows. And then we log the source MAC, and it's just a long, it's just 6 bytes of hex. So let's quickly do that. Okay, and actually we can copy paste this. We need to copy paste it 6 times. Actually, let's use colon, that's better, I believe. Hyphen is also fine, but I'll just go with colons. That's 5 and 6. 1 2 3 4 1 2 3, no, 1 2 3 4 5. So another one, that's it. And a new line, and we will just first log the source. Let's just copy paste this once again 6 times, and we will just change the indices 1 2 3 4 and it's 5. Okay, right, and then we print the destination MAC. So it's just a copy paste, though we'll have to change the struct property, but it's fine. That's destination MAC, and it will be h test. And we will, let's give our tab space to indent, and finally we will log the protocol, and we'll have to do once again into hs eth.h proto, and there we have our Ethernet logger. Next, and this will be a bigger one, let's log the IP header properties. Struct IP hdr star IP and a file star lf. Once again we'll print a header mentioning that the data following will be IP header data. So the first thing we'll be printing is the version. And then the IP header length. We have already used it to calculate the IP header length previously. We'll simply be logging it now here. And we'll be logging it in bytes. So we'll have to do that multiplication by 4 thing. So IP.ihl do 4. And then we have type of service. And we log the type of service, then so let me just copy paste this, and now we'll log, let's log the total length. Let's log the ID. And we'll call it identification. The property is just ID. We have got the TTL or time to live. And just note how all of these are 4 bytes in length. After that we have the protocol. After protocol we have the header checksum. Again, it's not necessary you will have to log everything. It's just that I'm logging in this case, but you can just log whatever you want to log. We could have even added a few more options from the terminal or from the get opts to take options from the user what to log and what not to log, but I'll just keep it pretty flat as of now, and we call it check. And finally we have got source IP. Okay, so we needed to do a, I believe, N2HS here, and here too we need to do a N2HS. So here we don't need this parenthesis. So the TTL is indeed 32-bit and the protocol is 32-bit. After the protocol we have the source IP, and for that we need to do inet into A, and we'll pass the source addr.syn addr, and we have our destination IP. So actually let's copy this line, it will be easier, and we'll call it destination IP, and we'll be using destaddr.synaddr. So that's all the header data, I mean most of the IP header data which we logged, right? Actually you can always check what all you can log. You can simply click on one of these, and yeah, we have pretty much logged everything. If you want, you can log this frag offset as well, but okay, I'll just leave it here. Okay, so now what we'll do is the next logger, or the next logger function that we'll create, is for TCP, and let's create a function for that. Struct TCP htr slash htr start TCP, and let's start logging the TCP header informations as well. So let's start with logging the TCP headers now, and this will also be a big chunk like IP headers. So let's start printing them out one by one. So we'll start with the most important ones, that is well, everything has its own importance in the TCP header, but we'll start with the port numbers. So let's first put a marker that it's the TCP header upcoming. Now first thing that we will do is source port. And again we will have to use N2HS, and it will be TCP arrow source, and then we can copy paste this, and this shall be destination port. One second, let's copy paste this, and we'll have the sequence number. Then we will have the acknowledgement number. And sequence number is actually long, so we'll use N2HL. Even for acknowledgement number, we'll use N2HL. Then comes the header length, and once again, header length, just like IP in this case, is variable. It gives you the number of D words. So the header length is located in this field called TCP DOFF. It's nothing but data offset. So it simply says that from this offset the TCP data part starts, but this field will give us the total length of the TCP header. Again, this DOF field, it gives you the number of D words, right? So number of 32-bit chunks present in the header in total. So it's basically D word in caps, right? So one word is 16 bits in Intel architecture or x86 architecture, and so D word is basically double word, which means 32 bits. So to get the number of bytes, so we'll say header length in bytes we'll just multiply this with 4 and we'll get the header length in bytes. After that comes a very important section of TCP, and that's the flag section, all the TCP flags. So let's one by one put all the flags. So let's add a marker saying that these are the flags and not just the, I mean, well, these are also usual fields of the TCP header, but let's put a marker anyways, and we'll call it something like, let's say, flags, right? And then the first flag that we will log is the urgent flag. We will typecast it to a uint 32-bit, or basically an unsigned int, and this will be called TCP arrow urg. Next comes the acknowledgement flag, or ACK, a very popular TCP flag. Then we have push flag, which is PSH. We have the reset flag, RST, which is used for resetting or closing the connection. These flags makes kind of TCP what TCP is, hence these are extremely important. And we have the synchronized flag, or SYN, or SYN, which is a part of the three-way handshake. Synchronize flag. We have the finish flag, or fin, also used for closing connections. We have the window size. And we have to do N2HS here. N2HS. TCP check. This is the checksum. And finally we have the urgent pointer. Urgent pointer is just the URG PTR. As far as I remember, the urgent pointer simply says from which offset the urgent data starts, but I might be mistaken there, but as far as I remember, that is what it means. Okay, so let's just recheck once. Urgent, we have urgent flag U32, UN32, acknowledged flag is UN32, UN32, and then we have window size. Window size is N2HS, checksum is N2HS. We have the urgent PTR, which we don't need to be N2HS. Okay, so now we have printed all the TCP headers. So as I mentioned, it's a mouthful, but we are done. Then comes the UDP header. UDP header. For the UDP headers, once again we have the struct UDP hdr star UDP, and the file pointer, which is LF, and we'll call it log UDP headers. And once again we can start with the header marker. Yes, and we'll call it UDP. Then we have the source and destination port, which is pretty similar to your TCP source and destination port. Everything remains same, just the header variable name changes. UDP. Again, UDP doesn't have that many number of fields, so we can check here. Not much. So let's quickly add all of them. So then we have the UDP length, I mean, UDP length, this field in the UDP header is pretty much a redundant field because the size of a UDP header length is always 8. So yeah, it's not much of an use, but anyways, we'll just log it. Then we have checksum, and this will simply be check, and we are done with UDP headers. And then finally we are at the part where we are going to log the payload. So once again we will create a function called log payload, and uint8t underscore buffer, we need the buffer. Now finally we'll be using the bufflen iphdr. So basically we will be needing all the header lengths in this part because we will be going to the end of the raw packet, that is the actual user data. We need the protocol as well because depending on the protocol we'll be using either the TCP header or the UDP header. Okay, so that will be uint8 underscore t protocol. We have the file pointer, and we also need the struct TCP hdr pointer here because we need to dynamically calculate the TCP header length, right? That's not a constant. So let's first sort out the transport layer header length because that will give us some trouble. Not trouble, but yeah. So we'll call it TCP protocol header size. So let's just assume it's size of struct udphdr by default, and if we find that the protocol is IP proto TCP, then what we'll do is we will calculate the header length, and that will be uint32 t tcpd, same thing what we did while logging it, 4, right? And now we have the protocol header size, I mean the transport protocol header size sorted, and now we need to find out the offset from where our data is starting. So first we have the starting point of our buffer, or the starting address of our buffer, which is simply buffer, plus the size of the Ethernet header, which again is a constant, and that will be struct ethdr. After Ethernet header comes the IP header. So for that we have a constant, I mean already calculated constant, which is iphdr length, which is this. Then comes the final header, which is the transport layer header, and which we just calculated, which is t protocol header size, right? So that's pretty much where the user data is starting. We also want the length of the user data, and that's is also kind of easy. We can call it remaining, something like remaining data size, and we say the total length minus pretty much this entire thing. So we can simply copy this, and we could have also pre-computed it and stored this part in a variable, but that's fine. It's just 3 things we are adding. That's it. And now let's fprintf lf marker for data, and we say for int I equal to 0, I less than remaining data size I plus plus, if so we will just print it in chunks of 16, like 16 per row, right? So after every 16 bytes we have printed out, we will just put a new line and go to the next line. So if I not equal to 0 and I mod 16 equal to 0, we just fprintf a new line, and then we say fprintf lf, pretty much the same thing for printing hex, which is %2.x and a space, and then packet data at index I. and we finally print a elif and a new line. We now have all the functions to log individual headers as well as the actual data. So let's one see where we left off here. Okay, so we are presently here now and we are ready with all our logging functions. So now it's actually pretty easy. All we need to do is call our functions, log Ethernet headers, then log IP headers, then if it's a TCP packet, we log the TCP headers. If it's a UDP packet, we log the UDP headers, and finally we log our data. And there we have it. That's our entire tiny packet sniffer within how much 320 lines of code. Even lesser, I believe, if we just remove this log and print statements. So let's see how it looks when we execute it. So this is my terminal, and we have one file that is sniffer.c or sniffer.c, however you want to call it. I would go with sniffer.c and gcc sniffer.c -o sniffer. Okay, we have a few issues. Let's see what these are. Okay, the first issue is in line 41. Let's see what I have done. Okay, IDR, ADDR. Okay, so it should be IFR and not IDDR. Next we have, okay, on line 104 it says that shouldn't be %d, and let's fix that. Line number 104, and that should be here, and of course it will be %s, and the last one is our typo in 109. It will be f printf. And now let's try to compile once again, and there is another in on line 128. Okay, and it compiled. Okay, so now let's see our sniffer, that is our sniffer tool, in action. And to see it in action, what we'll do is we'll spawn up a VM, isolated VM using QEMU, and then in that VM we will try to run our sniffer tool, and we'll try to capture some packets and analyze the packets, basically see what data it captures, what are the different property of the packets it captured, and finally we'll add some filters onto the tool while invoking the tool, and see how the tool behaves, right, whether it's capturing the desired packets or not. So for that, what I'll do is I've already spawned a VM, Ubuntu VM using QEMU, and it's a very basic VM. I've simply used a live ISO to live boot this VM, and I've installed some basic stuff like vim, gcc, whois, and curl, things like that, right? And the first thing that I'll do is so I've divided my terminal into 3 screens. In this vertical screen we'll view the log file, and these 2 screens will do other stuff like running the tool, scping, and all those kind of things. So let's get started. First thing we will do is I'll SSH into the VM. So the IP of the VM is 192.168.122.11. Right, and what I'll do is soon I'll show the network configuration of this VM in a moment, but first what I'll do is I'll create a folder called raw socks. I'll cd into it, And I'll do the same thing in this terminal as well. And here, before SSHing, what I'll do is I'll scp sniffer.c2 home ubuntu raw socks, and somehow it couldn't. Of course, Ubuntu at 192.168.2.11, right? And if we see, yep, that's here. I'll simply now do SSH in this terminal as well. And that's the wrong password. Okay, so now what I'm going to do is I'll first compile the sniffer.c code, and what I'll do is sniffer.c -o sniffer, and it got compiled without any issue, which is good. And next, the first thing I'm going to do now is run our sniffer tool without any filters, and we'll try to capture all the packets that's incoming and outgoing of our VM from the VM's interface, right? Let's do that. And also I'll change cd into raw sock here as well, and what I'll do is do a sudo. I need to do a sudo because it's raw sock, so I'll do a sudo /sniffer, and I'll give it a custom log file. So I'll do -f sniffer.log, and let's start capturing the packets. So the sniffer.log file has got created, and let's do a tail -f on it and see what's going on. And there you go, it has started to capture packets. Let it go on for some time, and I believe that's enough. Let's stop it. Okay, so now let's open the file and see what packets it has captured. Let's see the first packet. It says the source MAC is 5254.11a0a7eb. So before going to that, let's do RPA on our VM and see what interfaces we have. So we have got two interfaces. One is the usual loopback interface, and the other we have got is ENP1S0, which has got an IP of 192.168.122.11, pretty much the IP on which I did the SSH, right? And it has got this MAC ID. So if you see, it's pretty much this packet is a packet which is outgoing from this VM to somewhere else, basically to the host machine's bridge interface. And how we know that? So the source MAC is this A7EB, ending with A7EB, which is exactly the MAC address of the VM, right? Again, how is it communicating with the host machine? It's communicating via a NAT bridge. So the VM manager, I'm using Virt manager as my virtual manager, which is managing this Chemo VM. So the Virt manager has already created a virtual NAT bridge on the host, which has got a network IP of 192.168.122.1. So that's the NAT IP. So that bridge is acting as a virtual NAT device, and the VM is pretty much communicating that with that NAT bridge as a gateway. So that NAT bridge is pretty much a gateway for this VM, right? So, and we can verify it from here. So since it was an outgoing packet, so its source MAC is this. This is pretty much the MAC address of the virtual NAT bridge interface. So it's a TCP packet, and if you see, the source IP is 122.11, which is the address of the source, and the destination IP is 122.1, which is the NAT bridge IP. And if we come to the TCP, so what packet is this? So if we come to the TCP header, you see that the source port from where the data is originating on the VM is 22, which means that this packet is a part of the SSH connection, which is happening between the VM and the host machine. So pretty much this is the response to the commands I'm typing on the terminal. So these are the responses that is coming from the VM to the host via the SSH connection, right? So that's an outgoing packet. So this is again an outgoing packet. So yeah, this again is an incoming packet. How do I know it's an incoming packet? The source MAC is E8F8, right? So E8F8 is not our MAC, but the destination MAC in this case is our MAC ID, which is VM's MAC ID, and hence it's an incoming packet, and it's coming from the bridge source IP, right? It's coming from the bridge, and it's landing on our interface because this is our interface's IP. And the destination port is 22. So basically this packet is coming to the port 22 of the VM. So again, it's part of the SSH connection, but this is the data that I am sending from this terminal from the terminal emulator to the VM, right? And so on and so forth. This was pretty basic, and now what we'll do is we'll add some filter. What I would want to do next is add a filter such that I only filter out those packets which are outgoing from the VM, right? So only those packets which are originating from the VM's interface, and I can easily do that by filtering by the MAC address. So I'll say that capture all the packets where the source MAC address is the MAC address of ENP1S0. So basically I want to find all those packets which are originating on the interface ENP1S0, right? And just to keep things clean, I'll remove this log file. Let's do this, and now you can see that the source interface filtering is set to ENP1S0, and let's see if it's capturing something. It is capturing. Let's wait for some time, and let's close it. Let's close here as well, and now let's check. So now if you see, you will only find packets where source MAC is A7EB, that is the MAC address of the interface ENP1S0 on the VM, right? You will never find a packet here where source MAC is anything apart from A7EB, right? Like anything apart from MAC address ending with A7EB. So that's another quick example of MAC address filtering. Now let's do something different. So now what I want to do is I want to capture all those packets which are originating from our interface, that is ENP1S0, and which is going to the HTTPS port of our remote web server, right? So basically it should only capture those packets which is originating from our interface and going to the port 443 of our remote machine. Pretty much it should capture any packet which is a part of a web request, an HTTPS web request. So let's see how we can do that. So this time I could have also done -i ENP1S0 here, but what I'll do is instead I will do SIP. I believe it was SIP. Let's check once, and I'll also delete it here. Yes, I believe it was SIP. Let's quickly see. Indeed it was SIP, and what I'll do is instead of doing I will do --SIP, that is source IP, and I'll set it to 192.168.122.11. Again, I could have done -I could have used source interface filtering, but I'm just for an example, I am doing a source IP filtering. And also I will do -D port. So I'll filter by destination port and I'll set it to 443, and I'll also give -T to ensure that, again, -T is kind of redundant because HTTPS anyways uses TCP, but anyways I'll just put in a -T there. So let's see what it captures now. So if I do a tail on sniffer.log now, there is basically nothing. So now in order to capture some packets, what I'll do is I'll hit any website. So it can be any website, literally google.com, facebook.com, amazon.com, but I'll just start with google.com. And for that I'll use curl in this terminal. So I'll do a curl -l https, right, google.com. And the expectation is as soon as I hit this command, I should see a few packets get captured in this log, right, log file. Let's do that. And here we go. We got some packets captured here, right? If I do something like curl facebook.com, once again I got some packets captured here because these packets will satisfy the criteria that I have mentioned here. So I'll stop the tool and let's do a less, and I'll clear things up here. You can see the first packet, it's a packet that's originated at our source MAC, that is, it originated at our VM's interface, A7EB, and it's going to destination E8F8, which is the NAT bridge. Then we have got the source IP as our interface's address, and we have got a destination IP. Let's see whose IP this is. So if I do a whois, and put this IP, you can see its org tech name is Google LLC because I just did a curl to google.com. If I do a dig at 8.8.8.8 google.com, so it pretty much gives me the same IP address which curl must have used to resolve google.com to an IP, right? And you can see it's initially the TCP handshake is happening. It sends us a synchronized flag, and then so we are not capturing the packet that Google sending back to us because we only wanted to filter it by the source IP, where the source IP matches our VM's IP, interface's IP. So that's why we cannot see the SYN ACK flag. But then again, the host sends it the acknowledge flag, right? And finally, once the TCP handshake is done, we start getting data. Pretty much, if you see that, that's what it was. We just did one curl to Google. So that's for Google. And now I believe I sent another request to facebook.com, and let's see if we can find a packet from Facebook. It was towards the end, so let's try this one. So again, there is a packet outgoing from our VM to this IP 57.144.142.1, and let's do a whois. And indeed this is Facebook Net Engineering. This is managed by Facebook Net Engineering, right? So this IP belongs to Facebook, and we can verify that as well. Dig at 8.8.8.8, and we can use this IP. Sorry, we can use facebook.com, and indeed it is 57.144.142.1, right? So that's how we can filter packets. So yep, these are a few examples of how we can use this tool to sniff network packets and how we can use various filters to capture our desired packets. And this shows how useful and how powerful raw sockets really are. Like, you can use raw sockets to capture packets, create packets from, although we did not see in this video, but we can also use raw packets to create packets from scratch, create all the layers of a packet like the TCP header, the IP header, or the UDP headers from scratch to send the packets to remote machines. Basically, like, raw sockets gives you the power to create your own, to design your own network protocols and test it out in user land. So that's the true power and utility of raw sockets. So yep, that's what I wanted to discuss in this video and what I wanted to build. Let me know in comments if you guys also have used raw sockets and how you have used it and what purpose it solved in your case. That's it for this video. Thanks for watching, and see you all next time.